Alright guys, lesson 30, trigonometry and the Pythagorean theorem. Make sure you have this lesson in front of you so that way you can copy as we go. Alright, so in this lesson we're going to rewrite the Pythagorean theorem in terms of sine and cosine ratios and use it to solve problems. We're also going to write tangent as an identity in terms of sine and cosine and use it to solve problems. Alright, I don't think this lesson will be too difficult, but let's just go ahead and get into it. So in a right triangle with acute angle measure of our symbol that we use, the sine of the angle is 1/2. What is the value of cosine of the angle? Draw a diagram as part of your response. I would suggest that you draw your diagram first. Okay? For some reason, diagrams always help to figure out things. So go ahead and draw your first diagram. Alright, so here is my triangle. Now it tells me that I have an angle, and guys, it does not matter which angle you mark as the angle we're dealing with. Alright, you could have marked this angle or this angle, but just make sure that you're labeling it correctly. Alright, so it tells me that the sine of my angle is 1/2. Well, we know that means that it is the opposite over adjacent. So my opposite would be 1. I'm sorry, not opposite over adjacent, opposite over hypotenuse. And my hypotenuse would be 2. So it wants to know what is the value of the cosine. So I want to know what this is. Alright, so cosine of my angle would equal something. How could I figure this out? Well, since I already know 2 measures of my triangle, I can use the Pythagorean theorem to figure this out. Alright, so 1 squared plus x squared is equal to 2 squared. So I get 1 plus x squared is equal to 4. I'm going to subtract 1, and I get x squared is equal to 3. How do I find what x is equal? I take the square root of it. So x is equal to the square root of 3. So the cosine of my angle would be square root of 3. Alright, in a right triangle with the acute angle of the measure, the sine of that angle is 7/9. What is the value of the tangent of that angle? Draw a diagram as part of your response. Once again, go ahead and draw your triangle and label what you know. Alright, so here is my right angle. This time I'm going to go ahead and label this one. Alright, like I said, it doesn't matter which one you label, but we're just going to switch it up just a little bit. So if I know the sine is 7/9, so sine is opposite over hypotenuse, so opposite would be 7 over hypotenuse would be 9. Alright, so it wants to know what is the value of tangent of the angle. Well, in order to find the tangent of the angle, if you remember, tangent of an angle is, remember SOHCAHTOA, is opposite over adjacent. Alright, so I've got my opposite, I just have to find my adjacent. I can do that using the Pythagorean theorem. Alright, so let's go ahead and figure out this. So I have x squared plus 7 squared is equal to 9 squared. Alright, so I have x squared plus 49 is equal to 81. So x squared is equal to, I'm going to take my 49 over and subtract that, and I get 32. So I'm going to take the square root of that. X is equal to the square root of 32. Now I can simplify that because if you take 32, that is 16 times 2. So that's the square root of 16 times 2. The square root of 16 is 4 square root of 2. So my side over here is 4 square root of 2. So now I can find my tangent. Tangent is opposite over adjacent. We do not leave square root of 2 in the bottom. So I can multiply by the square root of 2. That gives me 7 square root of 2 over 4 times the square root of 4. Well, we all know that the square root of 4 is what? It is 2. So 2 times 2 times 4 is 8. So the tangent of my angle would be 7 square root of 2 over 8. Okay? Alright, so we use Pythagorean theorem to find our missing side in the first two problems. Alright, so let's go ahead and look at example number 1. The Great Pyramid of Giza in Egypt was constructed around 2600 BC out of limestone blocks weighing several tons each. The angle measured between the base and each of the 4 triangular faces of the pyramid is roughly 53 degrees. Alright, so the reason I tell you this is because figure 1 here is a model of this Great Pyramid. Alright? So we can kind of look at this and see what we can do. What common right angle was probably modeled in the construction of the pyramid in figure 2? We don't have a figure 2, and I'm not really sure why. But let me go ahead and show you what figure 2 would look like. That's kind of stumped me here because you're supposed to have a figure 2. So we're going to let this be figure 2. And this is what figure 2 looks like. What common right triangle was probably modeled in the construction of the triangle in figure 2? Use sine of 53 is approximately 8/10. Okay, so in other words, they want to know what were the measures of our sides. Alright, so how might I go about figuring this out? When they talk about what common right triangle, remember we have different right triangles, like a 45, 45, 90, a 30, 60, 90. We have some triangles that have common measures. So they just want to know common side measures. They just want to know what common triangle was used here. It may not be completely obvious. So let's kind of look at this in comparison to this, to the first two questions that we did. What similarities and differences do you notice between example 1, part A, and exercises 1 and 2? And so think about that, and what other representation of 8/10 may be useful in this question. Okay, so what you need to see is that the value of sine of 53 can be thought of as, well, what is sine? Opposite over hypotenuse. Alright, so the sine of 53 can be thought of as opposite over hypotenuse, which is equal to, well, they told us the sine of 53 was 8/10. So I can kind of look at it like this, okay? So let's go ahead and look at question part A, all right, using this fraction. To determine the common right triangle that was probably modeled in the construction of the triangle in figure 2, using the approximation of sine of 53 is approximately 8/10, means that we're looking for a right triangle with the side length relationships that are well known. Alright, so label the triangle with the given acute angle measure of approximately 53 degrees, as labeled in this figure. Alright, so since it is the sine, and we said that is opposite over hypotenuse, opposite would be 8/10, and hypotenuse would be 1. Alright? So now, how can we find the third side? Well, we can apply the Pythagorean theorem. Alright, to find this side here, we're going to do 0 and 8/10 squared plus x squared is equal to 1 squared. Alright, 0 and 8/10 times 0 and 8/10 is 0 and 64 hundredths plus x squared is equal to 1. So now I'm going to subtract my 0 and 64 hundredths, and I get x squared is equal to 36 hundredths. Take the square root of that, alright, 3600 square root of that is 6/10. So I know that my missing side is 6/10. Alright, so the side lengths of the triangle are 6/10, 8/10, and 1. What well-known right triangle matches these lengths? Well, this one's kind of difficult. You probably still can't figure it out. So let's kind of look at this. Sketch a right triangle with the side lengths of 6, 8, and 10. Alright? So if I sketch a triangle with the sides 6, 8, and 10. Alright? Let's think about what triangle this might match. Well, guys, divide these by 2. Alright? So this might match a 3, 4, 5 triangle. Alright? So this is one of our common triangles. Alright? So here, if I look at this, how might I get 6/10 from that? Well, if I divide 3 by 5, I get 6/10. What happens if I divide 4 by 5? I get 8/10. What happens if I divide 5 by 5? I get 1. So the common triangle is a 3, 4, 5 triangle. Alright? The actual angle between the base and lateral faces of the pyramid is actually closer to 52 degrees. Considering the age of the pyramid, what could account for the difference between the angle measure in part A and the actual measure? Well, guys, think about this. It was constructed in, 2600? Yeah, 2600 BC. So this triangle is over 4,500 years old. Alright? Think about something that has sat there that long. Alright? And think about the fact that the blocks weigh several tons. So it could be that the weight has shifted and settled, just like our houses shift and settle. And our houses aren't over 4,500 years old. But But even a house that's just, 30 or 40 years old will shift and settle. So therefore, that might account for the angle measure being different in what we thought. All right, so the triangle is over 4,500 years old. And the blocks weigh several tons. All right, the blocks are heavy. So the pyramid could have shifted and settled. Causing that angle to actually be 1 degree less than what we thought. Why do you think the architect chose a 3, 4, 5 as a model for a triangle? Well, perhaps they used it because it's the right triangle with the shortest whole number side lengths to satisfy the Pythagorean theorem. Number of different reasons. Alright, so let's go into a discussion for just a moment before we get to example number 2. Alright, so let me grab a piece of paper here. Let's look at this figure. This is the triangle we just were looking at. Alright, and we're going to look at this angle being the angle we're going to reference. Okay, so we're going to let this be such that the sine of our angle is 8/10. Before we were using an approximation, we don't know exactly what the angle measure is. But we will assign the angle measure that results of the sine of the angle as 8/10. We're going to use the label this because we don't know. Alright, so in the diagram, rewrite the leg lengths in terms of sine and cosine of the angles. Alright, so let's think about this. How would I rewrite this to be sine and cosine of my angle? Well, guys, which side shows me the opposite? So I would write this as the sine of my angle. Alright. And then cosine would be here. Since the value of sine of the angle is 8/10 and the value of the cosine was equal to 6/10, we can rewrite our triangle like this. The Pythagorean theorem states that for a right triangle with the lengths A, B, and C, where C is the hypotenuse, that the relationship between the side lengths is A squared plus B squared is equal to C squared. So apply the Pythagorean theorem to this triangle. Well, let's think about this. So I would have the sine of my angle squared plus the cosine of my angle squared would be equal to 1 squared. Alright, if I were just using the Pythagorean theorem and using sine and cosine of my angle, this is what it would look like. This statement is called the Pythagorean identity. This relationship is easy to show in general. Alright? So, if I were to actually redraw this triangle for a moment, and I would see, here's my things. So this is my opposite, this is my adjacent, and this is my hypotenuse. Alright? Referencing this diagram, let's use the Pythagorean theorem. Alright? So it would be opposite squared plus adjacent squared is equal to our hypotenuse squared. Alright? So I'm going to divide both sides by the hypotenuse squared. Okay? And this is why. I'm going to show you something. Alright, this was using our original Pythagorean theorem. Now I'm going to divide by hypotenuse squared. Look at what I have. And hypotenuse squared divided by hypotenuse squared gives me 1, right? Alright? What's opposite over hypotenuse? The sine of my angle. What's adjacent over hypotenuse? The cosine of my angle. And what was 1 squared? 1. So we have just proven the Pythagorean identity. Alright? Alright, in pre-calculus, you're going to use this notation, but you're not going to have to worry about so much right now. Alright? Alright, so, example number 2. We're going to discover a second trigonometric identity, and this identity describes a relationship between sine, cosine, and tangent. Alright? So, show why the tangent is equal to sine of an angle over cosine of an angle. Well, let's think about this for a second. Let's think about sine of an angle. Alright, so the sine of my angle, in terms of this diagram, would be A over C. Cosine of my angle would be B over C. Now, we've not dealt with tangent a whole lot, but tangent is opposite over hypotenuse. I'm sorry, opposite over adjacent. So this would be A over B. Alright? So, let's think about why would tangent of my angle equal the sine of an angle over the cosine of an angle? Well, if I take the sine and I put that over the cosine of an angle, I have a complex fraction. But what I can do is I can multiply everything by C to get rid of this denominator. Look what happens. I end up with A over B, which is why tangent is equal to the sine of an angle over the cosine of an angle. Okay? Alright. Exercise number 3. In a right triangle with acute angle measures of our angle, the sine of that angle is 1/2. Use the Pythagorean identity to determine the value of the cosine of the angle. Okay, so remember, we now know that the sine of our angle squared plus the cosine of our angle squared is equal to 1. Okay? So, if I know that the sine of my angle is 1/2, so I've got 1/2 squared. I do not know the cosine of my angle. to 1. All right, now how do I do this? Well, 1.5 squared is 1/4 plus the cosine squared of an angle is equal to 1. Subtract that 1/4. I get cosine squared of an angle is equal to 3/4. How do I find cosine? I take the square root of it. So I have the cosine of an angle is equal to the square root of 3/4. Now I can rewrite that as the square root of 3 over the square root of 4. So the cosine of my angle would be square root of 3 over 2, because the square root of 4 is 2. Okay? Not too difficult, hopefully. All right, given the right triangle with acute measure of our angle, the sine is 7/9. Use the Pythagorean identity to determine the value of the tangent. All right, so now they want us to determine the value of the tangent. All right, so the first thing we have to do is find the value of our cosine. All right, I'm going to end up running out of time, I think. But let's try this. So sine is 7/9 squared plus the cosine squared of an angle is equal to 1. All right, 7/9 squared is 49 over 81. I'm going to subtract 81 from 1. I get the cosine squared of an angle is equal to, when I subtract that, I get 32/81. All right, square root of this. So cosine of my angle is equal to the square root of 32 over the square root of 81. Square root of 32, we've already done that. Remember, it's 16 times 2. So that would be 4 square root of 2 over the square root of 81 is 9. All right, I cannot simplify that anymore. So now we figured out that the tangent is sine over cosine. So the sine was 7/9 over cosine is 4 square root of 2 over 9. All right, I'm going to multiply everything by 9. So I get 7 over the 4 square root of 2, multiply by the square root of 2, 7 square root of 2 over, square root of 2 times the square root of 2 is the square root of 4, that's 2. 2 times 4 is 8. So my tangent would be 7 square root of 2 over 8. All right, guys, hopefully it wasn't too bad. Have a great rest of the week, and we'll talk to you next week.